Picture this. It's 1966, and you're standing trackside at Laguna Seca. The ground literally shakes as a bright orange McLaren thunders past at 180 miles per hour, its exposed V8, screaming at 7,000 RPM. The driver barely lifts for the corkscrew. This isn't Formula One. This isn't NASCAR. This is Can-Am, the most insane racing series ever created. No rules on displacement, no restrictions on aerodynamics, no limits on boost. Just one requirement, 2 seats, though nobody ever used the second one. The Canadian-American Challenge Cup was racing's Wild West, where millionaire privateers battled factory teams with budgets that would make NASA jealous. And into this gladiator pit, Chevrolet dropped a bomb so devastating it would help kill the entire series. The engine that would break Can-Am started life as something almost mundane. The Mark IV 427 Big Block, a motor you could order in your Corvette if you checked the right boxes. But what Chevrolet's engineers did to this engine in the secrecy of their racing shops would push it so far beyond its street origins that calling them related is like saying a Formula One car is related to a Toyota Camry because they both have 4 wheels. This is the story of the ZL1 aluminum 427 and later its absolutely mental offspring. Engines that made over 700 horsepower naturally aspirated in an era when 400 was considered excessive. Engines so powerful they literally twisted chassis in half. Engines that forced rule changes, bankrupted teams, and ultimately contributed to the death of unlimited racing. To understand why Chevrolet's Can-Am engines were so revolutionary, we need to travel back to 1966 when the series began. Sports car racing in America was dying. The FIA's increasingly complex regulations had strangled creativity. Attendance was dropping. Then the Sports Car Club of America had an idea that was either brilliant or insane. What if we just didn't have rules? The Canadian-American Challenge Cup would be for Group 7 sports racers, 2-seat racing cars with covered wheels and basically nothing else mandated. No minimum weight, no maximum displacement, no fuel restrictions. Turbochargers? Sure. Superchargers? Why not? Multiple engines? Nobody tried it, but it wasn't illegal. The prize money was enormous, over $1 million for the series champion, which is about $9 million today. This attracted the best drivers in the world: Bruce McLaren, Denny Hume, John Surtees, Mario Andretti, Mark Donohue. Names that could command top dollar in Formula One came to Can-Am because the money was better and the cars were faster. And they were faster. By 1969, Can-Am cars were hitting speeds Formula One wouldn't see for another decade. The McLaren M8D could top 200 miles per hour on the Mulsanne Straight. These weren't sophisticated European thoroughbreds either. They were brutal machines, aluminum tubs with fiberglass bodies hiding massive American V8s. The early years were dominated by McLaren and their Chevrolet. Power. But here's where things get interesting. The problem Chevrolet faced wasn't making power. Their 427 Big Block was already a legend. The Iron Mark IV version made 430 horsepower in street L88 trim, and race shops were pulling 550 horsepower pretty easily. The problem was weight. Can-Am cars were feather-light, under 1/800 pounds in most cases. Hanging a 680-pound iron Big Block off the back upset the handling. McLaren was winning, but barely, and Chaparral, with their wild aerodynamic experiments, was catching up. Roger Penske was coming with his Lolas. Dan Gurney was developing his own cars. Chevrolet needed something special. Enter Zora Arkus Duntov, the father of the Corvette, and a man who understood that racing was about more than just horsepower. In 1968, he authorized development of the ZL1, an all-aluminum version of the 427. This wasn't just an iron block cast in aluminum. Every component was redesigned. The block itself used a different alloy than the heads. 356 T6, aluminum with higher silicon content for strength. The cylinder walls were thicker than the iron version. The main bearing webs were reinforced. Siamese cylinder bores eliminated water passages between cylinders for strength. The deck height was raised 0.024 inches to clear bigger valves. The camshaft bore was relocated. Even the bell housing bolt pattern was different. The heads were works of art. Rectangular ports flowed 360 CFM on the intake, 250 on the exhaust, numbers that wouldn't be matched by production engines for 30 years. The combustion chambers were redesigned for 12.5.1 compression, while still allowing clearance for the massive 2.19-inch intake valves. Valve angles were optimized for flow, not production convenience. The rocker arms were full roller units that reduced friction and allowed more aggressive cam profiles. The intake manifold was an aluminum high-rise unit that positioned the carburetor 11 inches above the block for better mixture distribution. Let me put that in perspective. The complete ZL1 assembly weighed 485 pounds, 195 pounds lighter than the iron version. In a sport where engineers spent fortunes to save 10 pounds, Chevrolet just deleted 200 from the heaviest component. The engine made 585 horsepower at 6,500 RPM in conservative street trim with a hydraulic cam. Race versions with solid lifters, bigger carburetors, and open exhausts made 650 easily. Some builders claimed 700. In a 1,650-pound Can-Am car, that's a better power-to-weight ratio than a modern Bugatti Chiron. But Chevrolet wasn't done. See, the aluminum 427 was supposed to be a production engine. They built 69 of them for Copo Camaros to homologate it for NHRA Superstock. Each one cost $4,260, about $34,000 today, just for the engine. For Can-Am, they could go completely insane. The first modification was displacement. The rules allowed unlimited size, so why stop at 427? Chevrolet bored the aluminum block to 4.251 inches and stroked it to 4.25, creating a 482 cubic inch monster. Then they went to 494, then 510. Eventually, they built aluminum big blocks displacing 534 cubic inches, 8.75 liters. These engines used billet cranks, titanium rods, and forged pistons that cost more than most people's entire cars. The valve train was from another planet. Roller cams with over 0.700 inches of lift, nearly 3/4 of an inch of valve travel. Duration exceeded 320 degrees at 0.050 lift. The springs were so stiff they required 300 pounds of pressure just to open. Rev limiters were set at 7,800 RPM, though brave drivers saw 8,200. At those speeds, each valve was opening and closing 65 times per second. The intake valves grew to 2.30 inches, exhausts to 1.94. Some teams experimented with sodium-filled valves for better heat dissipation. Others tried titanium to reduce reciprocating mass. The fuel system was equally extreme. While street 427s used single 4-barrel carburetors, Can-Am engines ran dual Holley dominators, each one capable of flowing 1,150 CFM. That's 2,300 CFM total, enough airflow to fill a basketball in less than a second. These carburetors had no choke, no accelerator pump, sometimes not even air filters. They were jetted so rich the cars shot 3-foot flames on overrun. Fuel consumption? 7 miles per gallon if you were conservative, 3 if you weren't. But here's where it gets really interesting. The McLaren team, Chevrolet's primary customer, started developing their own modifications. They discovered that by raising the deck height another 0.100 inches and using custom pistons, they could run even bigger valves and more radical ports. They experimented with different combustion chamber shapes, finding that a bathtub design with the spark plug biased toward the exhaust side made more power. They tried different header designs, eventually settling on 2.25-inch primaries, stepping to 2.5 inches, then collecting into 4-inch collectors. The sound was indescribable. Imagine 8 top-fuel dragsters firing in sequence. The cooling system had to be completely redesigned. Stock 427s ran 180-degree thermostats. Can-Am engines needed 160-degree units just to survive. Radiators were massive. Some teams ran 2 or even 3. Oil coolers were mandatory. The dry sump systems held 16 quarts of oil and circulated it at 80 psi. Oil temperature regularly exceeded 280 degrees. Some teams experimented with exotic lubricants developed for aerospace. Others tried primitive oil additive packages that would later become racing synthetics. The result was devastating. In 1969, the McLaren M8B with the aluminum 430 cubic inch engine won 11 of 11 races, not just one, dominated. Bruce McLaren and Denny Hume finished 1-2 in points, often 1-2 in races, sometimes lapping the entire field. At Riverside, McLaren qualified 2.7 seconds faster than the third-place car. At Road America, they were so far ahead that Bruce actually slowed down in the final laps to preserve the engine. The competition was demoralized. Ferrari sent a fact-finding mission and concluded it would cost $3 million to be competitive. They declined. But dominance breeds escalation. For 1970, Porsche entered with the 91710, initially with a 4.5-liter flat 12 making 580 horsepower. It was sophisticated, light, and well-balanced, but it couldn't match the brute force of the Chevrolets. So Porsche did something unprecedented. They turbocharged it. The 91730 eventually made 1,580 horsepower from 5.4 liters. But that was 3 years away. In 1970 and 1971, the aluminum Chevrolets still ruled. The engines kept growing. Jim Hall's Chaparral 2J, the infamous sucker car, used a 465 cubic inch aluminum big block making 680 horsepower. The engine was so powerful it required a completely redesigned transaxle. The original Hewland LG500 would last about 3 laps before the gears stripped. Hall had to commission a custom unit from Weissman with straight-cut gears and multiple oil pumps. The Shadow team experimented with a 494 cubic inch version that allegedly made 740 horsepower, though it never finished a race. The pistons would melt after about 20 laps at full throttle. Let that sink in for a moment. These engines were making naturally aspirated power levels that wouldn't be seen again until the 2000s. A modern NASCAR engine makes about 750 horsepower from 358 cubic inches with decades of additional development. Chevrolet was getting nearly the same from carbureted engines in 1970, and they were doing it reliably enough to finish 200-mile races at full throttle. The development costs were astronomical. Each aluminum block cost $3,800 in 1970, about $28,000 today. A complete race engine cost $15,000 or $111,000 adjusted for inflation. Teams would go through 3 or 4 engines per weekend. McLaren's annual engine budget exceeded $2 million. And this was just for engines. The cars themselves cost another fortune. A competitive Can-Am effort required $5 million per year minimum. Several privateers went bankrupt trying to keep up. The human cost was significant, too. Can-Am was dangerous even by 1960 standards. The cars had minimal crash protection, no roof, and speeds approaching those of modern IndyCar. Bruce McLaren himself died testing the M8D at Goodwood when the rear bodywork came loose at 170 miles per hour. Peter Revson was killed in a Shadow DN4. Lothar Mochenbacher was badly burned when his McLaren's fuel system exploded. The engines were so powerful they literally overwhelmed the chassis technology of the era. Drivers reported that at full throttle, the torque would twist the frame enough to change the suspension geometry mid-corner. The engines also pushed tire technology beyond its limits. Goodyear and Firestone engaged in a development war that saw tire compounds change every race. The tires would last maybe 30 laps before the tread literally melted off. Teams experimented with different rubber compounds for different tracks. Some tried nitrogen inflation for more consistent pressures. Others played with tire pressures so low the sidewalls would fold under cornering loads. Blowouts at 180 miles per hour were common. The unintended consequences rippled through motorsport. The technology developed for Can-Am engines trickled down to drag racing, where aluminum big blocks became the standard for pro stock. NASCAR teams studied the valve train development and adapted it for their smaller engines. The dry sump oiling systems became standard in every form of professional racing. Even the fuel system developments influenced later fuel injection designs. The aluminum casting techniques Chevrolet developed were later used for the LS series engines that powered everything from Corvettes to pickup trucks. But success bred its own demise. By 1972, the racing was becoming processional. McLaren won everything. Attendance dropped. Sponsors pulled out. The SCCA tried to save the series with equivalency formulas, weight penalties for larger engines, boost limits for turbos, but it was too late. The oil crisis of 1973 delivered the death blow. Suddenly, racing cars that got 3 miles per gallon seemed obscene. The final Can-Am race was held in 1974, though the series limped along in various forms until 1987. Looking back, the aluminum 427 and its derivatives represent a unique moment in motorsport history when there were truly no limits. Today's racing is defined by restrictions. Formula One has 1.6-liter engines. NASCAR mandates specific cylinder heads. Even drag racing has cubic inch limits. We'll never see unlimited development again. The insurance costs alone would be prohibitive. The speeds would be unconscionable. A modern unlimited series with today's technology would produce cars capable of 300 miles per hour. No track in the world could handle that safely. But perhaps that's the point. The aluminum Can-Am engines proved that given unlimited resources and unlimited rules, engineers will always push beyond what's reasonable. They'll build engines that twist frames, melt pistons, and bankrupt teams in pursuit of victory. They showed us the absolute limit of what's possible with reciprocating internal combustion, and that limit was far higher than anyone imagined. In just 6 years, they doubled the power output of racing engines. They forced innovations that we still use today. They created legends that will never be equaled. Modern engineers look at these engines with a mixture of awe and horror. The efficiency was terrible. Maybe 28% thermal efficiency compared to 40% for a modern racing engine. The emissions would fail every current standard by orders of magnitude. The reliability by today's standards was laughable. But the raw, brutal, overwhelming power was undeniable. These were engines designed for one purpose, to win at any cost. And they did so thoroughly that they destroyed the very series they were built for. The legacy lives on, though. A handful of original ZL1 427s survive in museums and private collections. They're worth more than most houses. A complete documented race engine recently sold for $450,000. The Copo Camaros with aluminum engines trade for over $1 million. Reproduction blocks are available from Chevrolet Performance, though they're sanitized versions meant for street use. The original race pieces are irreplaceable. There's something primally satisfying about an engine with no compromises, no catalytic converters, no fuel economy standards, no noise regulations, just pure, concentrated violence barely contained by aluminum and steel. The aluminum Can-Am engines represent the absolute peak of the philosophy, the most powerful, naturally aspirated pushrod engines ever built, creating sound and fury that will never be replicated. They were too much for their own good, but what a way to go. What's the most insane engine you've ever experienced? Drop a comment below and share your story. And if you want more tales of engineering excess and racing madness, hit that subscribe button. Until next time, keep those engines screaming.